Again, here is just a single set of data, and I've put the curve with it. All right, and what I want to point out to you here is that this middle part right there, that is the average, the regular old mean value. Okay, so in this case, that may be 0.9. Okay, but what's significant is that distance and that distance. Okay, now when we go over that distance right there, from here to here, and the other way, in this case, that distance is probably about 0.02. Okay, and we call that distance the standard deviation, and we use the Greek letter sigma for that. If we subtract one standard deviation from the mean and add one standard deviation from the mean, then it turns out that in that little zone there, that's where we have 68.4%. So let's use this idea and compare your results with the cat's results. If we say that your standard deviation is 0.02 and it contains 68.2% of the data there, the cat has a smaller standard deviation, perhaps about 0.01. Okay, so 68.4% of the cat's data is in a smaller range than your 68% of the data. So this gives us a way to compare. We can calculate a number to get those. All right. Now, I haven't talked about exactly how we calculate the standard deviation. Some of you will take a statistics course and you can learn the ins and outs of how that works. As far as we're concerned here in physics, we put the list of numbers into our calculator or into Excel and we push a button and it spits this guy out for us. It's pretty easy. So earlier I asked you about what we would say the answer is, and we might want to say something like, the answer is that the coefficient of restitution is equal to 0.9. But then we said, yeah, but that's just the average value. That's just the mean, okay? And so what we really want to do is to be able to say 0.9 plus or minus something. And that's where standard deviation can come in to help, okay? So the standard deviation tells us about the width of the distribution, which in this case is 0.02. And the standard deviation is what we call a robust value. So that means if you did 100 ball drops and got 100 data points, they would have a distribution like this. If you did 1,000 data points, they would have a distribution like this. If you did 100,000, they would have a distribution like this. The shape is going to be the same. So the value that you get for the standard deviation is robust. It doesn't matter how many data points that you take. As we're taking our data, if we could calculate the average every time we drop the ball, we would find that that average value wiggled back and forth just a little bit each time. Every bounce adjusts it just a little bit. But the more we do it, the less it wiggles back and forth. And that's very helpful if we think about how to specify an answer. So we want to know 0.9 plus or minus what? And the answer is plus or minus the standard error. Okay, so here's the answer. I'm going to cut to the chase. What we do to specify the value of the coefficient of restitution, or whatever we happen to be investigating, is we say it's the average value plus or minus the standard error. Like that. Now, the standard error is equal to the standard deviation divided by the square root of the number of data points. So the standard error is equal to this robust number that is the standard deviation. So it doesn't matter how many data points we take, divided by the square root of the number of data points. So do you see that the more data points we take, the standard error actually goes down, okay? No matter how many data points we take, it turns out, as we talked about, the standard deviation will be the same, but the standard error will not, okay? It's going to be going down because n goes up. So for our example here, we had, we can think of it like this. The standard error is going to be 0.02 divided by the square root of the number that we have. Okay, so let's pretend that n is equal to 100. So we do 100 ball drops, and that would mean that the standard error is 0.002 because the square root of 100 is 10. Okay. All right, so when we're pretending that we have 100 data points, we saw that the standard error was equal to 0.02. But let's suppose that we have 100,000. Then when we take the square root of n, we're going to get another factor of 10 smaller, like that. So the more data points we take, the smaller the standard error is. All right, so the average value is 0.9, just like that. So the situation that we have is if we have 100 data points, then what we say is that the coefficient of restitution is equal to 0.9 plus or minus 0.002. On the other hand, if we had 100,000 data points, then we can feel a lot better about the value for the coefficient of restitution and say that it's 0.9 plus or minus 0.0002. So it's a lot more precise. Less precise, more precise. Doesn't help us. We don't know if it's right. We don't know if 0.9 is the real value or not, but we can finally say something about the precision.